Electrical motors are the heart of automation industry. Almost every automated machine is driven by an electrical motor. Whether it is a conveyor system, linear actuators, robotics, induction tables, or AGVs. Even hydraulic and pneumatic systems are eventually powered by electrical motor. So if motor is not correctly sized, the machine will never perform efficiently. And this is why the motor selection and their sizing becomes one of the critical part of any machine design. But at the same time, the motor sizing is a complex engineering process. There are mainly 4 steps. The first step is selecting the right type of motor. And there are many different types of motors. Every motor is designed for different purposes. So first, we must decide which type of motor is suitable for a particular application. And then comes to motor sizing, which means estimating the required motor capacity. And that entirely depends on required torque, acceleration, and inertia of the particular mechanism. And every mechanism has different physics. Some systems are belt-driven, some are screw-driven, some are gear-driven, and some are directly coupled with motor. So the formulas and calculation of motor sizing also change from application to application. And on top of that, we also need to decide whether the application requires a gearbox or not. And then finally, based on calculated parameters, we analyze motor data sheet, their feature, and then we finally come up with exact motor selection from catalog. And if any of these steps are not done properly, it often leads to incorrect motor sizing. For example, beginner engineers often select wrong type of motor. Senior engineers often ignore acceleration torque or the linear motion inertia calculation, which leads to incorrect motor sizing. And many engineers don't even properly understand the motor data sheet. So in this video, we will master everything that we must know to correctly size the motor for almost any application. Plus, we will also cover the common mistakes that engineers make during each steps of motor selection and how to fix it. So let's start with the first step, selecting the right type of electrical motor based on application. To understand it better, we can categorize the industrial applications in 3 main categories. First is continuous, constant speed application. In these applications, the requirement is just start the machine, run continuously at a speed, and at the end, stop. There is no need of speed variations and precise speed control, such as belt conveyors, centrifugal pump, hydraulic pump, fans, blowers, mixers, grinders. In these applications, our first choice should generally a 3-phase AC induction motor. These motors are extremely robust, low maintenance, fan-cooled, and have very long operating life. Almost 70% of all motors used in heavy machinery are 3-phase AC induction motors. Now, if 3-phase power supply is not available, then single-phase AC induction motors can be also used in these applications. But compared to 3-phase AC induction motors, they are usually less efficient and less robust. AC induction motors are also available in compact low-power version, typically below around 200 watts. These motors are often supplied with integrated gearboxes, which is why they are commonly called AC geared motors. I have used those in miniature conveyors. Now, the limitation of all induction motors is their speed not stay perfectly constant. As the load increases, their speed slightly decreases. And they also have limited speed range capped by grid frequency and the number of poles in motor stator. Yes, with VFD, Speed can be varied to some extent, 60 to 110%. For example, if motor nominal speed is 1500 rpm, speed can be adjusted in between 900 rpm to 1650 rpm. Beyond this, many trade-off starts, and it's not suitable for long-time operation. It's start reducing the motor life. So in application where motion is continuous but wide range variable speed is required, BLDC motors becomes a better choice. Unlike induction motor, BLDC motor use permanent magnets instead of induced electromagnet, and their speed is electronically controlled instead of power frequency. So they can operate over a much wider speed range. But most industrial grade BLDC motors are typically designed up to around 4000 rpm. They can also maintain much more stable speed even under variable loading conditions. They are also compact and highly efficient and can easily run on low voltage battery supply like 24 volt DC. That is why BLDC motors are commonly used in AGVs, commercial EV scooters, and drones. It doesn't mean that BLDC motors are only operate at DC power. Industrial grade BLDC motor power supply are also designed for AC power. And now comes to the third category, applications where we need full motion control, such as linear actuator, robotics axis, CNC machines, 3D printers, camera system, where we not just need a speed variation, but we need precise position, controlled acceleration and deacceleration, quick start and stop, or just keep holding a position even under heavy load. In such case, there are mainly two options: stepper motors and servo motors. Stepper motors are known for providing moderate precision positioning at low cost. They operate on electrical pulses. Every pulse rotates the motor by a fixed step angle, and this is why they are called stepper motors. Most stepper motors have fixed step angle of around 1.8 degrees, which means one complete revolution required around 200 pulses. Stepper motors are suitable for moderate load application, but they are not reliable under high dynamic condition because most stepper systems operate in open loop. So if they miss the step under heavy loading condition, the system itself may not detect the error. Also, most industrial grade stepper motors have limited speed and torque capability compared to servo motors, and have big trade-off in torque at higher speed. So the solution is servo motor. Technically, a servo system simply means a device that operates in a closed loop feedback control. Therefore, this DIY brush DC motor is also a servo motor. But here we are specifically talking about industrial PMSM servo motor, permanent magnet synchronous motor. These motors are designed for highly dynamic response, high acceleration, and very precise motion control. This is why they are widely used in factory automation. The main feature of the servo motors is closed-loop operation using high-resolution encoders. These encoders continuously monitor motor position and help maintain very accurate control even under high dynamic loading conditions. There are mainly two types of encoder in servo motors: incremental encoders and absolute encoders. Incremental encoders lose their position reference after power loss, which is why homing is required during a startup and every time whenever power shut off. Whereas absolute encoders, which is little costly but always remember their exact position even after power failure. So homing is often not required. Now, apart from these, there are also many other type of electrical motors. But these four are the most commonly used motors in factory automation industry. AC induction motor for continuous constant speed, BLDC motors for variable speed control at higher efficiency, stepper motors for moderate precision positioning under moderate load, and servo motor for highly precision motion control under highly dynamic condition. But the motor selection is not only about selecting the motor based on their function, it's also about reliability and cost effectiveness. Otherwise, even if motor selection looks correct on paper but it still fail in real machine or becomes unnecessarily expensive. For example, you will often find a stepper motor in highly precise systems like 3D printers, whereas in industrial linear actuators, you will find servo motor. Even if where application is not require extremely high accuracy. So why we still prefer servo motor? Why not use a stepper motor? Because industrial automation and consumer product design follow different philosophy. In product design like 3D printer, the main goal is achieving acceptable functionality at lower cost. So company invest heavily in R&D to develop low cost solution and then mass produce it. Whereas industrial automation machines are usually custom designed, where reliability, continuous operation, quick changeover, easy maintenance, and easy reprogramming becomes more important than just reducing the cost. Now, another important point is before motor selection, first utilize the mechanical system properly. For example, let's say you need to design a heavy rotary indexing table with fixed angular positions. Now, logically, a servo motor can be directly used to precise induction. But because indexing tables usually have very high inertia, we need a very large servo motor to quickly accelerate and deaccelerate the table. So if the indexing positions are fixed, then instead of using a very large servo motor, why not use an indexing gearbox with AC induction motor? It can still provide precise induction, but at much lower cost. Now, before we move to the next step of motor selection, the motor sizing, I want to mention JLCMC motors and drives catalog. And they have recently added lead sign servo motors and motion control products. What I found interesting is they offer a wide range of servo motors from 100 watt to 1000 watt at very economical cost. JLCMC is not only provides motor and drive. JLCMC is one-stop source for almost all mechanical and mechatronics components used in your machine design. What I found particularly useful is they provide free 3D CAD files for almost all the components. Another advantage is their clear online code and delivery process, which helps to reduce the lead time during machine development. And with a large range of automation component, including motors, linear motion products, transmission components, and pneumatic products, it becomes much easier to source the multiple components from a single supplier. They are also currently running a special promotion on their linear motion products. So if you are working on automation equipment, machine design, or industrial projects, you can check out JLCMC through the link in my video description. They are currently offering $123 in welcome coupons for new users, so don't forget to check out them. Now, after selecting the right type of motor, the next step is properly sizing the motor. Motor size is usually expressed as power in kilowatt, watt, or HP. Now, power is simply the rate of doing work. And in case of motors, since the motion is rotary, motor power becomes motor torque multiplied by motor speed. So in order to estimate the motor power for any application, We must either know the required power of that application or the required torque and operating speed of that application. For example, if we're sizing the motor for a hydraulic pump, I'm not going to calculate required torque. Instead, I will directly estimate hydraulic fluid power, which is the system hydraulic pressure into flow rate. And then considering the hydraulic efficiency, we can estimate the required motor power. Whereas in mechanical system like conveyors, ball screw linear actuator, rack and pinion mechanism or rotary table, here to estimate the required mechanical power, we must need to calculate the required driving torque and operating speed of this mechanism. And then we can size the motor with appropriate factor of safety. So first, let's understand how to calculate the required driving torque of this mechanical system. So to drive any mechanical system, the total required motor torque is the sum of load torque and acceleration torque. Load torque is a constant torque required to continuously overcome the mechanical resistance during operation. It's mainly caused by gravity, friction, or external load acting on mechanism. For example, in a ball screw or a lead screw mechanism, driving load torque depends on axial load and a screw lead. Whereas in horizontal belt conveyor, driving torque depends on total load, friction, and roller radius. Similarly, in rack and pinion mechanism, driving torque depends on axial force, friction, and pinion radius. If you have noticed, these all load torque formulas are derived from torque equal to force into radius. And that's the mechanical load torque. Let's understand it with a belt conveyor example. Let's say we have a 10-meter long belt conveyor and the total load on belt is 650 kg and belt itself mass is 50 kg. So the total mass we need to move with the motor is 700 kg. Now the belt is supported by a well-finished steel sheet and the coefficient of friction between belt and sheet is 0.2. Usually in practical applications, it's range from around 0.1 to 0.5 depending on surface condition. So the total pulling force required becomes mu mg, which is 0.2 700 kg into 9.81, around 1373 Newton. Now the driving radius is simply the radius of driving roller, right? Let's say the roller diameter is 44 mm. Therefore, the roller radius becomes 22 mm. So the load torque T becomes force, pulling force, into radius. It will be around 30 Newton meter. And this is how we can calculate the load torque for all these different applications by just using these formulas. Or if machine is physically available, then we can directly measure the load torque using a torque wrench. For example, in belt conveyor or ball screw linear actuator, if we slowly rotate the driving shaft using a torque wrench, the torque measured just before the system starts moving is the load torque. It's simply equal to the torque required to overcome the mechanical resistance during operation. But in actual machines, we do not use the motor just to slowly move the system. We use the motor to achieve a specific operating speed within a specific time limit. So to accelerate the mechanical system from rest to operating speed, we need extra torque in addition to the load torque called acceleration torque. According to Newton's second law, for linear motion, acceleration force is equal to mass multiplied by acceleration. But as the motor motion is rotational, acceleration torque becomes moment of inertia multiplied by angular acceleration. Means faster we want to move the system to reach operating speed, the higher the acceleration torque required. And once the system reaches the operating speed, acceleration becomes zero. Therefore, now the motor only needs load torque. to continue running at constant speed. But as we always start the machine from rest, the motor must be sized for maximum torque required, which is load torque plus acceleration torque. And this is exactly where most engineers make mistakes. Most engineers either completely ignore the acceleration torque, or if they calculate the acceleration torque during moment of inertia calculation, they only consider the inertia of only rotating parts and completely ignore the inertia of the part which are moving linearly. For example, in belt conveyor, total moment of inertia is not only the inertia of rotating rollers, it also includes the inertia of moving belt and carried load. Similarly, in a ball screw linear actuator, total moment of inertia includes both the inertia of the ball screw and the inertia of the sliding mass. Now you may ask that Ayush, we know how to calculate the moment of inertia of the object which are rotating around their own axis. For example, in conveyor, we calculate the moment of inertia of these rollers as the rollers is rotating about its central axis. So moment of inertia will be half mr square. Let's say mass of each roller is 6 kg. Therefore, moment of inertia will be 0.00242 kg meter square. For two rollers, it will be just double. But how do we calculate the inertia of this mass which is moving linearly? So for the linear motion objects, we calculate the equivalent rotational inertia using energy equivalence. Linear moment of inertia is mass into A divided by 2 pi square, where m is linearly moving mass in kg, A is the linear travel per revolution, meter per revolution. For example, in ball screw or lead screw system, linear travel per revolution A becomes a screw lead. So the equivalent inertia becomes mass into lead by 2 pi square. Whereas in a belt conveyor, linear travel per revolution A becomes roller circumference. So the equation will simplify to mr square. Therefore, for this belt conveyor, moment of inertia of moving load 650 kg plus 50 kg of belt, total 700 kg, will become 0.339 kg meter square. Now, once we calculate the total system inertia, including linear inertia, the next step is determine the angular acceleration. And this is another area where engineers often get confused. That is, if acceleration is not given, not clear, then how much acceleration should we actually consider? Or the motor like AC induction motor where acceleration is not directly controlled, it depends on load only. So how do we estimate the acceleration? And without acceleration, we cannot calculate the acceleration torque. So the first thing we need to understand is every motor starts from zero speed and takes some time to reach an operating speed. No motor can instantly go from zero to full speed. So acceleration always exists, even if acceleration is not given or even if we do not need to precisely control it. Now in servo, stepper and BLDC motors, acceleration can be controlled precisely as per requirement. But if requirement is not clearly defined, we can simply consider a practical, quickly achievable acceleration, or we can say safe maximum acceleration, which can be estimated from how quickly a motor can achieve its full operating speed. For example, for servo motor, acceleration time is usually very small, typically around 20 to 50 milliseconds. For stepper and BLDC motors, it's generally around half a second or 1 second. But in AC induction motors, acceleration mainly depends on load condition. And practically, an AC induction motor should be powerful enough to reach the operating speed within around 3 to 5 seconds. Because if AC induction motor take too much time to reach the operating speed, it start heating up due to high inburst current during starting. Now, once the acceleration time is decided, we can calculate the angular acceleration from acceleration time and operating speed. So how do we calculate the operating speed of the system? So again, it depends on type of mechanical system. For example, in ball screw or lead screw mechanism, the rotational speed depends on the linear speed of the actuator and the lead of the screw. Whereas in belt conveyor, the roller speed in RPM depends on required conveyor linear speed and the radius of driving roller. For example, in this belt conveyor, for a belt speed 20 meter per minute and the roller radius 22 millimeter, the required operating speed comes around 145 RPM. Now, to calculate the acceleration, first we need to convert the operating speed from RPM to radian per second, which becomes around 15.15 radian per second. And since we are using an AC induction motor, we can assume an acceleration time of around 3 seconds. So the angular acceleration becomes 5.05 radian per second square, assuming uniform acceleration. Now, as the total moment of inertia of this belt conveyor system is 0.344 kg square, the acceleration torque becomes 1.74 Newton meter. So the total required driving torque becomes load torque 30 Newton meter plus acceleration torque 1.74 Newton meter, around 31.74 Newton meter, or approximately 32 Newton meter. So finally, we have the required operating speed 145 RPM and the maximum driving torque 32 Newton meter. Now the problem is AC induction motors are designed to operate near specific speeds, which is mainly depends on supply frequency and number of poles. For example, a standard AC induction motor may run around 1500 or 3000 RPM. But not exactly at any random speed. So to match the required operating speed, we need to use a gearbox. For example, if we select a 4-pole AC induction motor, its operating speed is around 1500 RPM. A 4-pole induction motors are generally a good balance between speed and torque performance. So the required gearbox ratio becomes operating speed divided by motor speed, which would be around 1:10 ratio. Now with the gearbox, the operating speed becomes around 150 RPM, which matches our required conveyor speed. But a gearbox do not only reduce the speed, it's also multiply the motor torque by the same ratio. That means we do not actually require a motor capable for producing 32 Newton meter directly. With a 1:10 gearbox ratio, the required motor torque becomes 32 divided by 10, around 3.2 Newton meter only. Now, considering the gearbox efficiency of around 90% or a factor of safety of 1.5, the required motor torque becomes approximately around 4.8 Newton meter. And now we can also calculate the motor power. And this is where most engineers make mistake. They use the motor torque but multiply it by system operating speed. But if you are using the motor torque, then we must also use the motor speed, which is around 1500 RPM in this case. So the motor power becomes 753 watt or 0.75 kilowatt. And now we have finally all the required parameters, required motor torque, speed, power, and the gear ratio. So now we can select the motor from manufacturer catalog. For example, here we can select 0.75 kilowatt motor. Its rated torque is 5 Newton meter, whereas our required motor torque is around 4.8 Newton meter. And its operating speed is around 1425 RPM, which is also acceptable. If required, we can fine-tune the speed using a VFD. Now, for AC induction motor selection is quite straightforward, but things becomes more interesting when we selecting a servo motor or other motion control motors. For example, in servo motor catalog, you will usually find two torque rating, rated torque and instantaneous torque. So here the rated torque should always be higher than the load torque, whereas instantaneous torque should be higher than the total required torque, which is load torque plus acceleration torque. Now in stepper motors, available torque decreases significantly as the speed increases. So in case of stepper motors, it's not enough to check only the rated torque. We must also check the torque speed curve to verify how much torque of the motor can actually deliver at the required operating speed. This trade-off is much less significant in case of servo motors. That's the one more benefit of servo motor over a stepper motor. Now, unlike AC induction motors, servo motor can operate over a wide range of speed, simply at any speed from 0 to maximum rated speed. So in many applications, we can directly achieve any operating speed without any gearbox. And this leads to an important point. For servo motor, gearbox selection is not only about adjusting the speed and torque. Very often, it becomes a question of cost. Should we use a larger servo motor directly or use a smaller servo motor with a gearbox? And that decision also depends on inertia. In fact, this is the point where most engineers make mistake. Most engineers think a gearbox is only used to reducing the speed and increasing the torque. But in many applications, even where motor already have enough torque, a gearbox is still necessary to significantly reduce the inertial load seen by the motor. So before selecting a gearbox, first we need to understand the real purpose of the gearbox in motor selection. And this is what we are going to cover in next video. Next video should be on your screen, or you can check the video description. And guys, thank you so much for making this award possible. I mean, you guys are literally changing my life. So thank you so much for subscribing the channel, liking the video, commenting on the videos, or sharing my videos. And I hope I will keep making more and more useful videos for you in future. Thank you so much for watching this video and for this award.